this STERIS Tech Talk on accelerated aging and real-time studies. My name is Noel Gibbons. I'm a technical advisor on packaging and testing in Galway facility.
And my name is Wilhelm. I'm the manager of our product and package testing group in our Brooklyn Park, Minnesota facility.
So today's talk is on accelerated aging and real-time studies and how to perform them and what the requirements are in around the standards. But before you do any studies or of any sort, you need to understand, have you the correct packaging? Because it's no good getting part of the packaging solution correct and then ending up with something like the picture that's shown on the screen. This box traveled approximately 80 kilometers, and you can see the state of it after that duration. So if you imagine that sitting in an aging chamber in high humidity for 2, 3, 4, 5 years, or the equivalent of, it wouldn't perform reliably for its expected lifetime. So you wouldn't have the right packaging there. So the questions that you need to be able to ask and know the detail behind is, what is aging? What is the purpose of the aging testing? What causes product and packaging to age? Do I need product in the packaging for aging studies? A very, very common question. And yes is the answer. I would always recommend having product in there because if you don't have product in there and you age an empty package, you have nothing to do functional testing on your packaging, and you have no information on your actual product. What is the glass transition and melt temperatures of a material? Again, very important to know, and you'll see later on in the presentation why that is the case. Again, another very important subject in relation to, say, the likes of papers and polymers, all materials really, is what about relative humidity? When does accelerated and aging, real-time aging have to be carried out? What risks are involved, and how is the shelf life, or how long is the shelf life of your product? We'll be addressing those throughout the presentation. They may not be in that exact order, but bear with us, okay? So in relation to some of the standards, ISO 11607 Part 1 states that packaging systems shall provide physical protection and maintain integrity of the sterile barrier system. So, what that means is that the sterile unit must maintain intact until the point of use or until the expiry date that's shown on the packaging. And this is carried out by doing stability testing that demonstrates that the sterile barrier maintains its integrity over time. And the way that is done is by using accelerated aging protocols, which shall provide sufficient evidence to claim the expiry date so you can actually commercially release the product. That data then from the accelerated aging is then valid until the real-time aging studies information or data is available, and the post-accelerated and post-real-time aging studies to prove that the integrity of the packaging is still there. If you look at a graphic of ISO 11607 for Part 2, you have everything there from DQ or design qualification, IQ, OQ, PQs, and the process there of assessing the packaging throughout the whole process. So you do, say, the likes of your IQ or your OQ, you'll do, say, the likes of seal strength testing. So you're establishing what your seal strengths are. For your process validation, then you do package integrity testing and seal strength. So as you know that your process is not going to cause any issues with the packaging and the seal strength is still valid and that you have a good range in there. Then you have your baseline or T0 testing from your production samples, which have also been sterilized and gone through a sterilization process. The sterilization process is a whole process by itself with a lot in it, which we're not going to look at today. Then you have your distribution and your validation of your packaging and how it works through the distribution cycles. And again, you have the likes of your package integrity and your seal strength testing that needs to be carried out at that stage. And finally, but what we look at there next is the shelf life validation, or your accelerated aging and your real-time aging, and what has to be done there. So you might be wondering why you need to do all this seal strength testing and package integrity testing all the way across. Basically, what you're doing is you're comparing what happened at your OQ and your PQ levels to what's happening out at the end of your shelf life or your aging. So you can show that the seals and the integrity of the packaging has not degraded over time. What is shelf life? Shelf life is basically the length that a product may be stored without becoming unfit for use, unfit for consumption, or unfit for sale. And it must be able to demonstrate the ability of the packaging system to maintain the integrity and strength over a defined period of time. This time period, this duration, is normally labeled on the product, and it's used by or noted by an expiry date on the actual packaging itself. Shelf life is actually determined not by the lab, not by a regulatory body, but by the manufacturer of the product. It's not solely a chemical makeup of the materials, but it also includes the likes of the manufacturing processes, the product material types, the packaging material types, and the packaging that it's contained in, how the product is to be stored. Basically, where is it going to be stored? Is it controlled conditions? Is it uncontrolled conditions? Or how is it being done? A very important thing also is the package product dimensions, because if you have a large product in a very small pouch, which some people try to do, that product is putting pressure on the seals and will damage the seals over time. And last but not least, in determining the actual shelf life, is sales and marketing, because they determine how long the product is actually going to be on the market for. And that they have a big say in that decision. If you look at accelerated aging itself, it's basically an artificial procedure for establishing the shelf life. It's a guesstimate on the useful lifespan of a product when the real-time data is not available. It's carried out by simulated exposure of the product to elevated temperatures and humidities. Again, looking at the F1980 standard, or ASTM F1980 standard, the maximum temperature you can recommend to use is up to 60 degrees, unless you have further data on the actual product and the materials within the product and packaging to show that it's not going to degrade over time. Accelerated aging, the expiry date that you get from that is tentative until the results from the real-time aging are available. And that includes the integrity and seal strength testing that's normally carried out after the aging study. While real-time aging itself is a pure stability testing. So it's basically the product sitting on a shelf for a period of time, whatever you have defined, whether it's 1, 2, 3, 4, 5, or 10 years, whatever the case may be. Again, you're using both temperature, a set temperature, a set humidity. You can, if you wish, age the product in your own warehouse in uncontrolled conditions, but it's not recommended for a very simple reason. If you're not going to monitor both the temperature and humidity levels, you don't know what the product and packaging has been exposed to. New or modified devices or products must be storable. Again, they must be available for use at the point of use without deterioration after real-time aging. If you're looking at artificial aging, what causes products to age? It's basically what happens is you're stimulating the materials to speed up the normal aging process to basically release the product, so you can have a commercially available product at a much shorter time. The typical examples of accelerators are sunlight, oxygen, heat, vibration, chemical, and relative humidity. Again, as I said, accelerated aging is optional. It gets you to the market very fast, but real-time aging is required when establishing the expiry date. We've come across certain circumstances where a product is manufactured on a Monday, it's shipped on a Wednesday, it's used by Friday. So again, accelerated aging or real-time aging studies are absolutely of no use to in that situation. You'd need it for much longer term. In relation to regulatory bodies, they will recognize the accelerated aging data as acceptable, and they'll take it in for you to release the product. But you must follow that up with the real-time package product data, and the outcome of the integrity and seal strength tests on that. As again, the primary focus here is on the sterile barrier system to make sure that it will maintain its sterility to the point of use or until the expire date. And the challenge and how you challenge it after the aging process, again, is back down to what you decide as in your risk assessment is that the product can take. Typically, as I mentioned already, that would be the likes of bubble leak testing, dye penetration testing, seal strength testing, burst testing. Those type tests are typically what's used. If you look at the calculations for accelerated aging, what we use and what's defined in the AST MF1980 standards is the Arrhenius reaction rate, or the Arrhenius Equation, which basically states that if you increase the temperature by 10 degrees, it doubles the chemical rate of reaction. So it's basically halving the time that's in there. This is based on the premise that deterioration of materials and services due to chemical reactions and kinetic energy within the actual product itself. There are 4 variables that are used when calculating the accelerated aging. Their temperature, that's the accelerated temperature, the ambient temperature that you use. Typically, that's a conservative value of 25 degrees as stated within the ASTM standard, but you can have other values which we'll look at shortly as well, and I'll give you some reasons why. The Q10 value, or the reaction rate factor, is normally for medical devices set to 2. We'll have a look at that shortly as well, and the actual duration in days of the real-time days that you want the package to last for. The Q10 value, or the reaction rate factor, as I said, is normally set to 2, but you can use more aggressive ones as well, from 2 to 2.5 as per the standard. But you must have a very well characterized product in there and packaging in there. The level and the nature of the damage that you get from these raised Q10 levels must be very similar to that reported in literature or your knowledge of the product from previous studies. And again, assigning the appropriate Q10 factor is the responsibility of the manufacturer of the product, or the owner if it's an outsourced product. And again, it's very important to understand what this does. So if we look at the formula that's given for accelerated aging, the accelerated aging factor, or the AF, is the part of the formula under the line, what you're actually using to divide into the time that you want to actually assess. So if you have, say, for example, an accelerated aging temperature of 55 degrees and an ambient temperature of 25 degrees, your accelerated aging factor will be a value of 8. That's what it'll actually calculate out to. So you can very easily and very quickly define what your actual accelerated aging factor is going to be. This basically increased the chemical reaction rate and caused the accelerated aging to happen. One thing you must note is that the accelerated aging must be performed prior to distribution of the product, or prior to release of the product commercially. Okay. If we look at the graph here, showing you the various temperatures, if you look over on the left-hand side, you have the 22-degree temperature there on the bottom. If you use that temperature, or 23 degrees, it's going to take you approximately 52 weeks to do 1 year accelerated aging, which wouldn't make a lot of sense. Whereas if you look over on the right-hand side, where we're using up as far as 60 degrees, you can do accelerated aging of 1 year in approximately between 4 and 5 weeks. Okay, so it's a huge advantage to be able to increase the temperature of the product. Typically, what's used is in or around 50 to 55 degrees for most studies, because you're getting towards the edge of the upper level of 60 degrees, which is not favored by the regulatory bodies, because in the standards basically states that above 60 degrees that the aging factor becomes non-linear. Okay, If you have the drug-encoded product, you will need to be in around 38 to 48 degrees. Again, that will depend on the product that's coated onto it and how the temperature will affect the efficacy of that product. If we look at a little more detail and play on what you can do to actually manipulate or play around with the actual formula. As I said, if you use an accelerated aging temperature of 50 degrees with an ambient temperature of 25 degrees, a Q10 of 2, your accelerated aging factor then will work out as 5.66. So if you divide that 566 into 365, it basically rounds up to 65 days that the product would have to be in the chamber. If you make a slight change to that formula where you would decrease the ambient temperature by a couple of degrees, you can see that the accelerated aging factor has now gone up to 6.50, but it's also reduced the actual time in the chamber. And again, if you do change the accelerated aging temperature up to 55 degrees, as I said earlier, with an ambient of 25, your accelerated aging factor is now 8. Again, it's gone up again. But it's also, the cause of that has actually reduced the overall duration down to 46 days. And again, you can play around with the figures until you get to what you want to establish as your accelerated aging duration. The problem with that is that you have to justify what you're doing and every change that you make. You have to justify your aging temperature, you have to justify your ambient temperature, and you also have to justify what Q10 value you're using. So if you can see there from the start of 65 days down to the last one where it is 29 days at 60 degrees, that's a significant saving in time in a study. And time to release to market and cost of testing. But the problem is there that it is a couple of months saving. Is it worth a risk? So your risk evaluation plays a huge role here to see what's going to happen with that. The other thing you must note there is that accelerated and real-time aging studies should start within 3 months of each other. So you're testing the same basic lot of packaging and the basic materials as well of the product. Some of the effects of aging are based on shippers, on outer shippers. If you have high levels of temperature and high levels of humidity in the actual chamber where the boxes are exposed to, the manufacturer's joint can fall apart. So if this happens in real life, which it quite often does, your courier is going to come along, he's going to wrap that up in lovely, his tape, branded tape with your name on the box, and it'll get to you very, very not nice condition. Again, that's with high humidity. The opposite will happen if you have, like on the right-hand side there, a corrugated board will split if it gets too dry. This is actually an after test, after aging. You can see it in the center where there was a concentrated impact done and the whole box just fell apart. It just broke. You could actually push your fingers through the actual corrugate. So from there, I'll hand over to Nate for the next part of the presentation.
All right, thanks, Noel. So how do you know what an appropriate accelerated aging temperature is? And what you look at there is the melting glass transition temperatures of the material. So you're going to look at the physical properties of your product and the packaging. So TM is the melting point or the melt temperature, and that's the point above which the crystalline regions in the semicrystalline polymer are able to flow. Semicrystalline polymers begin to soften above TG, which is the glass transition temperature. However, they do not demonstrate fluid behavior until TM range is reached. So typically that melting point is higher than the glass transition point. And at temperatures between the glass transition point and the melt temperature, there is a rubbery region. So this region, materials can exhibit large elongations under relatively low loads, and so basically they can be very easily deformed. So that glass transition temperature is the temperature at which a polymer transitions from a soft rubbery state to a rigid glassy state if you're reducing the temperature. Only amorphous polymers or the amorphous regions of semicrystalline polymers exhibit that glass transition temperature. So if you take a look at this picture here, this was straight when it went into aging. And you can see that this product was aged above its glass transition temperature. So we reached that rubbery state, and you can see how that product has been deformed over time. So the specifications and material properties should be considered for all materials when you're choosing that accelerated aging temperature. So you can see in the graph here, it's really illustrating where that glassy state is there at the top, your glass transition temperature on that downward slope there, that rubbery state in the middle up until your melt temperature, at which point you reach a viscous flow. It's important to note that the polymers may not return to the original state if you've gone beyond that glass transition temperature when you cool them back down. So there can be changes in the polymers. Obviously, if the material deforms, it's not going to go back to the shape that it once was. You can see in the table here on the right some glass transition temperatures of some common polymers. You can see, you know, the PET, PETG, relatively low, 73 C, up to some higher temperature ones in the HDPs. So you can see why it's important to take a look at this kind of information prior to choosing that temperature that you're doing your accelerated aging at. So these photos here, again, this customer did not take into consideration these temperatures on their material. They aged their product at a temperature that was above both the glass transition temperature and the melt temperature for the polymers in their product. And basically their product and the packaging was completely melted and destroyed. So what about relative humidity as it relates to accelerated aging? Noel mentioned earlier that this is something you want to consider. How do you determine what the appropriate humidity level is? So the equation that Noel showed earlier did not include relative humidity. It's not a factor in determining the aging duration. That equation is based only on temperature, as he showed. But heightened relative humidity can create defects that are not related to real-time stress. And low-level relative humidity can cause defects that are not related to real-time stress as well. So humidity is a real use condition, and it can result in degradation of polymers, hydrolysis, corrosion of metal materials. And so it definitely needs to be considered in your accelerated aging. So how do you choose that humidity level? It should be chosen to avoid damage or changes to packaging materials that would not be expected during real-time aging. So high levels of humidity can cause boxes to soften and become easily damaged. Noel showed some photos a few slides ago of boxes that were splitting and had clearly degraded due to that humidity. But low humidity can also cause packaging to drop and become brittle, as he also demonstrated in photos. So realistic RH levels are recommended for polymers in shelf life studies unless there's a specific reason for using other humidity conditions. And that's going to be based on the knowledge that you have of the material, previous studies that you've done, R&D work that you've done. The ASTM F1980 standard for accelerated aging suggests levels between 45% RH and 55% RH. And if other conditions are used, a rationale should be documented in your accelerated aging protocol. So let's go through here a last slide of some practical guidance for determining the representative aging test conditions. So your first step is going to be to select that Q10 value. As Noel mentioned, the standard recommends using 2 as a conservative level. That's very commonly used. If you choose to use anything other than 2, you really need to have a well-characterized system and have a lot of data to support that choice. You're going to define the desired shelf life. As Noel mentioned earlier, there's many factors that go into what that desired shelf life is. You're going to define the aging test time intervals, including time 0. So you're going to almost always want to test some sort of interim time point. So if your ultimate shelf life is 5 years, you might also want to test 1 year, 3 years, and 5 years, just to have some interim time points in the event that a later time point might fail. Or you could also go to market with a shorter shelf life to start and ramp that up as you get additional data going on. Next step, you're going to define the test conditions for real-time aging, and you're going to define the test conditions for accelerated aging. You're You're going to decide if humidity conditions are required, again, based on your knowledge of the materials, whether there's any hydrolysis that might happen, whether there's any corrosion that can happen to your device. Choosing a realistic level of humidity is recommended. You're then going to use that Arrhenius equation to calculate the test duration for your accelerated aging. You're going to define the sterile system material properties. So again, those material properties are going to help determine humidity conditions, what appropriate temperatures are, things like that. All of this needs to be documented prior to you starting. So generating a study protocol and having that approved internally at your facility prior to beginning this testing is what the regulatory bodies are going to expect to see. You're also going to define your acceptance criteria, things like that in that document. You're going to then start to age your samples at your accelerated aging conditions and at your real-time conditions. Again, as Noel mentioned, these should be going concurrently. The regulatory bodies will accept your accelerated aging, but they expect to see that real-time aging is in process as well. You're going to define those acceptance criteria in that protocol that I mentioned. And then after the aging, whether it's accelerated or real-time, you're going to evaluate that sterile barrier using the package integrity testing and seal strength testing to ensure that you're meeting the acceptance criteria that you defined in your protocol. And you're going to compare those results to time zero and PQ results. So that's really going to be defined in your protocol. Those acceptance criteria are often based on the results obtained during that performance qualification that you did during the sealing process validation, or at the results obtained at time zero. And that's how you're going to determine whether there's been any degradation that could negatively impact your sterile barrier. So I just want to finish this webinar by reiterating that the sterile barrier system is part of your product, and it's a key to protecting the patient. It does need to be considered part of your product, should not be an afterthought. All this testing goes into making sure that that product maintains its sterility and maintains its functionality for the life of the product. So I want to thank you for watching this video. This concludes the webinar.